So today we're going to work on chemical reactions. We're going to start with a review for precipitation reactions and oxidation reduction or redox reactions, and then we'll do a brief introduction to acid-base. Finally, we're going to end with stoichiometry, so I have quite a few stoichiometry problems I want to do with you. If we do run out of time, which is highly possible, I recorded videos of me solving all three of those stoichiometry problems. So whether we get to them or we don't get to them, you have access to the full solutions. So let's get started with the first one. We want to write balanced net ion equations for these three word equations. So what I want you to do is pause the video and write as best you can the net ionics for these three things, and then on the next slide I will go through the answers with you. Okay, for the first one I wrote potassium chloride, which is aqueous, silver nitrate, which is aqueous, and this is a double replacement, so we now have potassium with nitrate, and because it's a nitrate we know it's going to be soluble, so you're going to write AQ, and then we have silver with your chloride. That isn't one you have to memorize, but since it's telling you that you are going to make a precipitate, then we know this one has to be the precipitate. But it would somehow there'd be some clue that you know one or the other, and we know this one's definitely soluble. Okay, so what I really care about here is what's going on with this one. So we're going to break everything up into ions. That is aqueous, right? And then we're going to keep together the solid. So the next thing that you want to do is you want to actually cross off the spectator ions, the ones that are on the same on both sides. Oops. And you are left with the chloride ion, the silver ion, and you are making silver chloride. For the second example, I have lead 2 nitrate, and that's aqueous, whoops, and we have sodium iodide, which is aqueous. So my positive ions are going to switch places, so now my lead is going to combine with my iodide, my sodium is going to combine with my nitrate, so we get sodium nitrate and lead iodide. Nitrates are still aqueous. This one will be our precipitate. And then you have to go through and you have to actually balance this equation. Okay, next step will be to break everything up into ions. So we have, we have lead 2 plus, we have 2 nitrates, because there's a 2 there, we have 2 sodium ions, we have 2 iodide ions, we have 2 sodium ions, right, because there's a 2 in front, we have 2 nitrate ions, and then we have lead iodide. So then the next step is to cross off the things that are just spectating. They are just watching. Nothing's happening. And then you write what's left. So I have lead 2 plus, 2I minus, and we're going to get lead iodide. All right, here is my unbalanced, so my skeletal equation. Sodium hydroxide, aluminum nitrate, sodium nitrate, it's a nitrate, it's going to be soluble, and my aluminum hydroxide. So then I need to go through and balance. Okay, after you balance the equation, then you're going to break up your ions. So I have 3 sodium ions, 3 hydroxide, I have an aluminum with a +3, and 3 nitrates. So sorry this is small, it's hard to fit it all on one screen. And then I have 3 sodium ions, 3 nitrate ions, and I have aluminum hydroxide. So then you go through and you cancel out your ions that are the same on the left and the right. So those are your spectator ions. And then you write what's left over. So I have 3 hydroxides, 1 aluminum, and that's going to give me aluminum hydroxide. That's my net ionic equation for this reaction. Okay, so here is the answer key if you wanted to see it in a little larger print here. So on the PowerPoint, you will have a link to AP daily videos if you needed another review of your net ionic equations. So let's just kind of go back. So we have hydrogen often does a reaction where if I put a metal in water, I'm going to release hydrogen gas. And so what we had started to talk about at the end of last session was these redox half reactions, and it's just showing you half of what's happening. So I just wanted to do it again. So here we have sodium and water making sodium hydroxide and hydrogen. And what you notice here when you're asked to write the reduction half reaction, that means only write what's happening with the species that's reduced. In this case, your oxygen is being, your hydrogen is being reduced. So hydrogen is with water. So you want to write the water. So I have my water. And in this case, you're gaining electrons to make your hydrogen gas. Okay, so you don't have to worry about balancing. I just want to show you what it looks like for a half reaction. And then if I wanted to look at the oxidation half reaction, we are losing electrons. So your sodium is going from no charge to a +1 charge. Okay, so my sodium is going to a +1 charge and it's losing 1 electron. So the reason why I wanted this particular reaction shown to you is not that you have to know how to balance these. If you notice, this is only the loss of 1 electron in this reaction. However, up here, I have 2 electrons. So in order to actually get this equation to balance, I'm going to need to have my 2 electrons. So in this case, we have 2 electrons being gained, 2 electrons being lost. So part of what you want to recognize isn't just which one's being reduced, which one's being oxidized. We want to make sure that the number of electrons is equal, because if you look at the reaction up here, it's not balanced, right? I have 2 hydrogens on the left, 3 on the right. Okay, so this is an unbalanced, so it almost is unfair. I probably should have put the balance to begin with. So if we wanted to kind of look at these, what they would look like on top of each other, you have your reduction half reaction, you have your oxidation half reaction, and just like with net ionic equations, if it's on the left and the right of the arrow, they cancel. So you can see I'm on the left of the arrow, the right of the arrow, it cancels, and this is your overall equation. Okay, so we write 2 half reactions, we can add them together to get the whole overall reaction. Now, what's really cool is sometimes you can have an element that has more than one oxidation state, so it can undergo both oxidation and reduction at the same time. So let's look at one of those. We have iron, a couple different oxidation numbers. We have solid iron added to a solution of iron 3 chloride, and we make iron 2 chloride. So the first reaction we have this iron ion 3+, and it's going to iron 2+. So in order to go from 3+ to 2+, you have to gain an electron. So you see how on this half reaction, I wrote it like this. The other iron, this iron is a solid. We only have one product here. This iron that's a solid is also changing to iron 2+. So we start with a 0 oxidation number and then we go to a 2+ oxidation number. In order for that to happen, it had to have lost 2 electrons. Okay, so see that magic, that top one changed? If you look, I have 1 electron on the left and 2 electrons on the right. So that's just not quite going to work. We need to transfer 2 electrons to be balanced. Okay, so if we multiply everything on this top line by 2, like right here, you can now cancel your electrons. I have 2 electrons on the left of the arrow, 2 electrons on the right of the arrow. So if you add everything up for your balanced chemical equation, I have no idea why I switched the order on these. We have 2 iron ions, we have an iron solid, and we're making 2 + 1, 3 iron 2 ions. Okay, so another example of how you can use those half reactions to write the overall balanced equation, because this is not quite showing the full picture. You can tell it's not balanced just by looking at your chlorines here. Okay, so just to kind of review redox reactions, there you can look at the AP Daily video 4.9. So now we're going to get to the introduction of acid-base reactions. And so this, remember, there's a whole unit dedicated to acid-base. So we just want to do kind of the bare basics so you can recognize it as an acid-base reaction, which is one of the 3 types of acid-base reactions. So the first scientist to actually coin the term acids and bases, his name was Arrhenius. So you have a definition called the Arrhenius definition of acids and bases. And basically he said, if I'm an acid, when I go into water, I'm going to break up into H+ ions. If I'm a base, when I go into water, I'm going to break up into OH ions. Well, that's simple enough. So that covers actually most of acids and bases, but it doesn't cover all the acids and bases. There are some bases that don't have hydroxide ions. So we need a new definition. Okay, so Bronsted and Lowry, 2 different scientists, came up with the next definition of acid bases. Acids are going to donate protons. Bases are going to accept protons. And this is going to cover most of the items that we're looking at. So this is the definition that we go with. And so that's why they ask, what's the Bronsted-Lowry acid? What's the Bronsted-Lowry base? That's what they're doing. They're asking you for the acid or the base based on their definition. Acids are going to donate protons. That means the H+ is going to fall off, and bases are going to pick them right back up. Okay, so if we have a reaction, here's a generic one. I have an H, and A could be anything, a whole bunch of different stuff. And then we have a base, labeled B for base. The acid is going to lose this H+. So that's why on the right-hand side, you see A-. And the base is going to gain the H+. So over here, you see BH+. Okay, so we're just kind of transferring that H+ back and forth. So this acid on the left, on the right-hand side, it's at equilibrium. This A- can then take that H+ and come back to HA. So it's acid-base pair, if you will. So here's the acid, and here is its conjugate base, meaning on the right-hand side of the equation, it can now act as a base. Here's the base, and this is its conjugate acid. Okay, so this is saying the exact same thing. You may be asked what's the conjugate acid-base pair, and they want you to pair these up. So the conjugate acid-base pair in this case for the base would be B and BH+. All right, so let's look at this balanced equation. Okay, pause the video and see if you can identify which is the acid in these 2 reactants and these 2 reactants, and which is the base. After you identify acid and base, then I want you to go through and identify its conjugate acid and its conjugate base. So go ahead and pause the video, and then I'll show the answers. Okay, so if we look at this first one, your acid has the H. Now this one also has an H, right? But I'm going from HNO2 to NO2-. It lost an H. So that must mean this is the acid. And this is its conjugate base. Water, if I look on the left and compare it to the right, it gained an H+. That's the definition of your base. So that's why this is the base, and this is its conjugate acid. When you go to the second one, you look at ammonia, NH3, and it gained an H+. Well, that means this is the base, this is its conjugate acid. You look at water here, it starts as H2O, and on the right it ends in OH, which means it gave up an H. That's your definition of an acid. And here is its conjugate base. And so this is a great example because water is something called amphoteric. It can act as an acid or base, depending on what else is in solution. We'll learn a lot about strong acids, strong bases, weak bases. At this point in time, you need to know that if it's a strong acid, it's going to completely give up every single H+ when it gets into water. They call that 100% ionization. When we talk about equilibrium, you'll see it as this, meaning I don't go backwards. This A- doesn't pick up any H's to become HA again. It's a strong acid. And then weak acid, you'll see 2 arrows here because not all of the H+ are taken up by water. Some of them stay on the acid. Okay, so there are some strong acids you have to memorize. we're going to see HCl and nitric acid and sulfuric acid all the time. These here on the left are not as common, so just kind of add them to your list of things to memorize. And then for strong bases, almost all 1A, so group 1A, alkali metals, when they're with a hydroxide, they're strong bases. Now, magnesium hydroxide is not a strong base. We can talk more about that later, but calcium, strontium, barium hydroxide are all strong bases. This is a super quick intro to acid-base. Make sure you can identify who the acid or base is and what their conjugate acid-base pair would be. All right, so now we're going to get into stoichiometry review, and I did these on the Show Me video. So I'm going to stop this amazing presentation, I know, and then when you go into the stoichiometry review, you can click on this and you will see the worksheet. I don't want to make a copy. You'll see this worksheet. So I give you the problems, and then I use the box method to show you how to solve all these problems.